My name is Neil Henry, and I was in the Greenland class for this past semester. And for my final video, I'll be talking about question number 3, which is the historical, present, and future climate change that we see over the past 1,000 years. So to begin, I'll talk about proxies. And so basically, there are two proxies that are really dominant when we're talking about climate change in the past 1,000 years. The first of which is ice cores. And so the reason why we use ice cores, it has to do with the reason because they have high resolution. And they can be calibrated with temperature records in 018 ratios within the ice. And something that's important about ice cores is that they can be dated with layering counts and volcanic eruptions. And so basically what we look for in an ice core is we look for different volcanic eruptions that we know have happened. Say there was a volcanic eruption in the 1950s. We would look for that specific ash and we'd be able to tell where exactly it is in the ice core. And so that's how we can date it with layering counts. And the reason why ice cores are important is because we can basically find the main thing is the bubbles in the ice cores. We can find what the temperature was actually like during specific periods of times, and because it sequesters like CO2 and it sequesters the atmosphere in those bubbles, so we can actually see what the atmosphere was like and compare that to temperature. And so another proxy that we use is tree rings. And so the reason why we use tree rings is because it has high resolution. The important thing when we're talking about tree rings is they only work when they're stressed. You can only see changes when they've been through a bad time. And so that's also how they're calibrated. So they're calibrated with temperature and precipitation associated with ring size. And so if you have a tree that's been growing in perfectly good conditions, you're not going to get the changes in the ring sizes that you want to see. We can find out different temperatures because, say, if we find a year where ring size, or a year or two where ring size is very small, we might be able to associate that with precipitation and temperature, an increase in temperature. Another important thing with tree rings is you can use mass spectrometry to see carbon levels in the atmosphere at a specific time. Now, the reason why this is important has to do with the fact that carbon in the atmosphere is associated with the temperature that it was during that time. So in the past, what would happen is you'd have an increase in temperature, and then you'd see an increase in carbon right after that. And so this correlation between temperature and carbon can be used to figure out the temperatures. And so the big picture when talking about these proxies is that proxies are regional. So you have to piece them together. And one region might tell you something completely different than another. An example of this would be the Little Ice Age, where we had spots of cooling and of cold ice age like temperatures in the northern hemisphere, but in the southern hemisphere we didn't see that, and it was very regional. And so you have to piece them together in order to get a bigger picture. If you just use proxies from one area and you just assume that that's what the whole world looks like for temperature and the climate at that point, you're not going to have an accurate representation of global temperature. And so if we're like kind of moving on, talking about hemisphere-wide and global temperature in the past 1,000 years, we need to weave these proxies together. And the reason why we do that is because proxies have different weight to them. You need to actually understand the proxy itself, and because there's seasonality differences within proxies, you need to make sure you understand that for specific ones. And so basically you need to know what the proxy is telling you about the climate, and you need to know where you found this as well. And so if we're talking about temperature changes in the past 1,000 years, we have to talk about this graph right here. And so basically what this graph is showing us is there was a plateau pretty much, except for a few dips and a few increases throughout the past throughout the past 1,000 years. And then there's this increase, and then a little dip, and then an increase again. This little dip happens to be in the 1960s. And so what happened right there is before the 1960s, we relied off of proxies and human data, people just going out and saying what they thought the temperature was like at that point. And we pieced them together and made this graph. Now, if you see right there, it starts to increase. Now that's during the post-industrial era, but that's still pre-1960s. And so what was happening there is we see an increase, and this is actually the hockey stick curve. And so the reason why there's a little decrease there, it doesn't have to do necessarily with it cooling, because but it could also have to do with better taking atmospheric temperature directly. And so we can see an increase in temperature from industrial era going up. And if you take a look at different graphs of CO2, methane, other greenhouse gases, we see the same effect, where it was a plateau, and then it kind of just skyrockets after industrial eras. And so the important thing to talk about this graph is that these are all this is proxies of temperatures in the northern hemisphere. We do have proxies from the southern hemisphere, but they're very little. And the proxies that we do have from the southern hemisphere show us the exact same thing, pretty much, where we have this plateau for a very long time, and then it just increases post-industrial. And so if we're talking about all this, we want to know the importance of this. And so we need to talk about models and climate models in order to understand the bigger picture and what lies ahead in the future. So basically what a climate model is, it's a mathematical representation of the climate. And what you do is you take the laws of physics and what you know about the natural world, and you put it into a program. And with this program, you can put data into it. So, for example, let's say you want to know how much of an effect the anthropogenic forces are going to have in future climate, like say our increase in greenhouse gas. So what you do is you would take an estimated amount of greenhouse gas, let's say for example 100 parts per million of carbon more than what we have now. You'd put that into the model and see what the outcome would be. And so in order to almost calibrate and make sure that these climate models are doing what they're telling you to do correctly, you have to look at past climate. So what you can do is, let's say there was a time period where you knew there was a specific amount of methane released into the atmosphere, and that caused a specific change in temperature. Now you know how much methane was put into that system, and you know what the outcome was. So let's say you take a climate model and you put that specific amount of methane, and you get a result back that was completely different from what actually happened. That model is no good. That's why we look to the past in order to make sure that our climate models are saying what they're supposed to do. Now, if the other way around, let's say you put the methane amount in and then the outcome was the same of what happened in the natural world, that's going to be a good model to use. Now, you don't just use one model either. You take a bunch of models and you almost average them out. By looking at just one model, you're not doing yourself any good, because models are never correct. And so we need to look to the past in order to test to see if these models are actually working and doing what they're supposed to be doing. So what lies ahead in the future? The IPCC has been working on models, and they've been working on stuff that will help us to see what lies in the future. And so the IPCC came up with 4 scenarios. And these can be described in this graph right here. And so basically the IPCC came up with 4 scenarios. The first is business as usual, the 2 is a mitigation strategy, and the third is 2 moderate scenarios. And so we can see these in this graph. The orange represents business as usual. The purple pretty much represents a mitigation strategy. And what we can see here is in the orange we see an increase in CO2, like a tremendous increase in CO2, which leads to an increase in temperature. And then the mitigation strategy still has an increase, but it's not as great as business as usual. And so the reason why this is important is because in both graphs we see an increase in temperature. It doesn't matter if we start mitigating them, we see an increase in temperature, and that's around 1.5 to 4.5 degrees increase in the future. And so we're going to see effects from this increase in temperature. It just matters of the magnitude and scale that we're going to see. And so something that the IPCC really needs to take in consideration when using these climate models is that they can't take in consideration small or abrupt changes in small scale processes. An example of this could be something as simple as permafrost. We have increased temperatures, which melts the permafrost, which can increase the methane levels and cause a positive feedback to increase more temperature. We don't know the scale that that's going to be at. We know it's going to happen. We just don't know how much it's going to actually affect our climate, if it affects it at all. Another example, this is the THC feedbacks. We know a lot about the THC, but we know very little about what is going to actually happen with the THC with increased temperature. Like, we know that it will slow down, but we don't know to what degree. And so with all of this in consideration, you have to realize that models are never correct. The only correct model is the Earth itself, because that's real life. And so taking all of what I just said into consideration, we have to look at the big picture and see that over time we can use proxies to put into a model and see if the outcome will be positive or negative. And so, our future lies ahead and we don't really know what's going to happen. But, we're working on it. So it's been a great class. I really enjoyed this class, and I hope to see you guys in the future. Thanks.